So this is some work that we've been working on with Arup Ganguly, my advisor Ravi Sundaram, and Devesh Tiwari. So the title of the talk is Resilience and the Coevolution of Networks. And I'm going to start off with a motivating example about what we're talking about. So many of you may remember the 2012 blackouts in northern India. So essentially the power grid collapsed in numerous states after a cascade of failures that were precipitated by many individual events. So you can see on the map here, the affected areas are in red, and the dark red areas are where power was lost for 2 days, and light red is where power was lost for 1 day. And the reason for this was many different factors. So one of them was extreme heat in Delhi that led to record high power consumption. And also we had late monsoons, which led to increased power consumption for irrigation pumps in Punjab and Haryana. And also because of the late monsoons, we had low hydroelectric power. So as a result of these disparate events, we had failures in the network of the power grid, which led to more nodes failing in the network, and this sort of cascaded on. So the question we can ask from this is, can we characterize the relationships between these different events that led to such a collapse of the entire network and sort of learn about network resilience from this? So in fact, there was another study done a couple of years ago on the blackout in Italy in 2003, which was studied by Boldyrev et al. And they essentially characterized the actual real-world data by modeling it using network science. And so you can see here, we have the map of Italy, and each stage here sort of explains the collapse of the power grid and internet communications network. So you start off here with around Rome, where there was a failure in one of the power grid. So the grid on the map here itself is the power network, whereas the network up here on the side is the internet communications network. So when you had a failure here with red, it sort of corresponded to some failure in the power network, the internet communications network, and this led to more failures in the green here. So then in the next stage, after these failures occurred in the internet communications network, that propagated to more failures in both the power grid and the internet network. And slowly, as you go, from step to step, you have this cascade where you have failures bouncing back between the two different networks. So, as a result, Boldyrev et al. Analyzed this failure and tried to characterize network resilience properties that you can get by modeling this using some techniques from network science. So I'll just quickly review some of the concepts, and we can get started. So in network science, we require that we have a distribution over networks that allows us to model the lack of information that we have in the real world. And initially, people modeled these by what are called Erdős-Renyi graphs, or networks, which uniformly sort of sample from all possible networks that can exist. However, it turns out that in the real world, we don't really have networks that look like Erdős-Renyi networks very often. And so people were searching for a better way to model these graphs. And in particular, they were interested in something called the scale-free property. So in 1999, Barabasi and Albert discovered a method to generate these scale-free graphs. And by scale-free, I mean that if we look at the fraction of nodes in the graph that have degree k, this is proportional to k to the power minus gamma. And so essentially, this is what we call the degree distribution. And it forms what's called a power law. And the term scale-free here comes from the fact that if I take the ratio of the degree distribution for, like, say, degree 2k and k, then I actually end up with a constant factor here, 2 to the minus gamma. So no matter how big my graph is, it could be 1,000 nodes, 1,000,000 nodes, the ratio of the number of nodes with 2 degrees is always constant. And that's where you get scale-free. So here I have a diagram showing the degree distribution of Erdős-Renyi graphs and scale-free networks. So here we have this drop-off that starts off very high and falls off really quickly. This is the power law that we get from scale-free graphs. And over here we have the degree distribution for Erdős-Renyi, which follows a Poisson distribution. So now that we have some of the basics down for network science, we can look at the study of interdependent networks, which is essentially the problem we're looking at with these blackouts in the examples that I gave before. So in particular, Boldyrev et al. Models the power grid and the internet communications network as two separate scale-free networks that are interrelated in some manner. And the way that they model this is, once we have these two networks, we connect them randomly. So you assume that the number of nodes in each network is the same, and then you connect each node to another node in the other network uniformly at random. And however, the issue with this is that, again, in the real world, networks sort of evolve together. They're not completely independent of each other. So you can't just generate a power network and an internet communications network and not expect that the designers sort of had in mind the hubs of the internet network and put a power plant near those hubs to power these stations. So instead, our goal here was to try to find a way that model two networks that grow sort of together with varying amounts of correlation. And we like to term this as evolutionary correlation, because as these networks evolve, they sort of grow off of each other and respond to how the other network is behaving. Let me present our model. So we're going to generate two scale-free networks, but we'll start off by doing only one of them. And we're going to use the standard Barabasi-Albert model of generation, which is what they introduced in their 1999 paper for generating scale-free graphs. And so the way it works is we first start off with an empty network, no nodes, no edges, and then we add nodes one by one sequentially. So I can add one node, add a second node, add a link to this, and add more nodes. And essentially, the way that I'm connecting these links as I keep adding them is proportional to the degree of the node. So in other words, the probability that I connect to some node I that occurred before is the degree of that node divided by the sum of the total degrees. And of course, it's important to remember that we only connect to nodes that have already been added to the network, not nodes that will be added at a future date. Let's call this network A. And for the second network, we're going to call this network B, is going to generate in a similar fashion, except, of course, we're going to take into account how network A behaves. And we're going to measure this interconnectedness using a parameter alpha, which ranges from 0 to 1. And so, again, network B will be on the same node set as network A. This is to allow us to model things sort of cleanly and nicely. And again, we're going to sequentially add nodes to network B, but this time we're going to change the order in which nodes arrive. So you can think of the nodes that arrived in the first network as arriving, node number 1, node number 2, node number 3. But now this time, I'm not going to put nodes in that, increasing order, but rather the probability that I pick a certain node to go next is proportional to both this 1 over what I call n over r, which is the number of remaining nodes in the network, and of course the degree of the node itself in the first network, network A. So, and then I'm essentially just using the alpha parameter here to interpolate between these two distributions. So you can think of this as sort of mixing together uniformly picking and picking with respect to a certain degree. So the reason why we do this in a different order is that it captures the different ways that we can connect the networks together. So furthermore, now we can talk about how to add edges to this network, and we're going to do this proportional to degree, but not just the degree that we have before, but now we have two types of degree, local and global. So global here refers to the sum of the degree in both network A and network B, and local just refers to the degree in network B. And again, we define the probability to connect to a specific node as just interpolating between these two extremes. So here I have the degree L here referring to local degree, and here I have degree G referring to global degree. So we can think of the alpha equal to 0 case where this term sort of disappears completely and we only look at the degree, global degree, as being similar to generating like a big Barabasi-Albert network with twice the number of edges. And we essentially, make one pass, add edges, and then we iterate one more time and add more edges together. And this is essentially what happens at alpha equals to 0. And you'll have to note that the node arrival is sort of not guaranteed to be exactly the same, but with high probability it will be. And then, of course, the alpha equals to 1 case corresponds to the model from Boldyrev et al., where you have two networks that are generated independently because, of course, this term dies. And so we only care about local degrees. So essentially, network B doesn't even know network A exists and just forms independently and connects with probability proportional to local degrees. So let me quickly get into the disaster and recovery model. So we're going to view the global degree of a node as its wealth. And we're going to break it up into 3 groups. We have poor nodes, which are low degree nodes, middle nodes, which are medium degree nodes, and rich nodes, which are high degree nodes. So the disaster model here is we're going to kill all rich nodes. And by kill, meaning we just deactivate the nodes in the network, but they still remain in there. And then for recovery, we want to revitalize all these nodes that were deactivated. And we're going to do this by saying that the middle class will support all the rich class, the rich nodes that died. And they're going to share all of their wealth, aka their degree, with each failed node equally. So they divide it up equally, and then they transmit the wealth from them to each rich node. But as the resource travels through the network, it drops off by a factor of the distance. So we just divide by the distance it takes to reach the node. And the more resource that a rich node receives translates to a higher probability that the node will recover in one time step. So we ran some experiments on this model, and this is sort of what we received here. So on the bottom x-axis, we have this alpha parameter, which ranges from 0 to 1. And on the y-axis, we have recovery time. And so note that the big Barabasi-Albert network sort of has the highest recovery time up here. And the Boldyrev network has lower, but it's not the lowest on this end. And rather, we have the optimal recovery at around alpha equal to 0.8, which is a little bit curious because one would initially sort of expect that the Boldyrev model, because of the randomized connections, sort of already hides the vulnerable parts of a scale-free network, which tend to be the hubs. But instead, what we have is that some amount of correlation between the two networks actually gives you better resilience properties. So let me just conclude by saying that I gave you a parametrized model which studies co-evolving scale-free networks, and we're interpolating here between a large scale-free network and 2 independent scale-free networks. So we're getting the extremes of like full correlation of growth and completely independent. And we showed that the resilience properties of our model, that randomizing the links for the networks does not give you the best resilience, but rather semi-dependent evolution leads to better resilience. And so some future work that we would like to look at is, can we obtain a closed form to describe the degree distribution of our model, which would help explain exactly why these, semi-dependent evolution is what gives you greater resilience. And yes, that's all I have for you today. Any questions? Yeah.
So you are not doing it on any real data?
Not yet. So we're first trying to,
Any idea how it will work on real data? This will hold, or most probably this Boldyrev will be the best one. It will be difficult for you to implement that, and it looks that it is very close to that.
Yes. So so first off, one of our motivations is that we have lots of networks in the real world that they don't actually collapse that often. So you have these artificial networks like the power network, which have vulnerabilities, but we see networks all the time that end up being pretty resilient. So that was sort of our motivation. And then going back, you can always look at the degree distribution of a real network and then sort of infer what the alpha parameter is from there and sort of analyze it that way.